Section: Introduction. In this section, we discuss the significance of video understanding in computer vision, which has been a long-standing goal. Video benchmarks have progressed from evaluating short action recognition clips to more sophisticated assessments that analyze longer videos, thanks to the emergence of multimodal large language models. These models are now capable of handling complex video tasks and are nearing human-level performance on recent benchmarks. However, while these datasets measure video understanding, they do not explain how models arrive at their answers or why they might fail. To better understand model failures, we can look at the step-by-step reasoning generated by the models. Efforts to enhance these rationales have shifted the focus towards models that engage in more thinking or reasoning, particularly in the text domain. In contrast, reasoning in the video domain is more complex due to the high dimensionality and multiple modalities involved. Solving video tasks often requires identifying key objects and actions over time and applying logical reasoning to connect these elements. This multi-step process, which we call a reasoning trace, is essential for video question answering. Despite the multi-step nature of video reasoning, current benchmarks only evaluate final answers, leaving us uncertain about whether a model's correct answer results from effective reasoning or mere chance. Similarly, if a model fails, we cannot determine if it was unable to solve the problem or just made a critical mistake. This reliance on final answers complicates the creation of challenging datasets as models rapidly improve. To address these issues, we introduce MINERVA, a benchmark for video reasoning that includes questions, answers, and reasoning traces. MINERVA is designed to be challenging, requiring multiple steps to answer each question. Even the top-performing model achieves only 66.2% accuracy, while humans reach 92.5%. The dataset encompasses various video types and lengths, ensuring diversity. For each question, we provide a detailed reasoning trace that outlines the necessary steps to arrive at the correct answer. Unlike other datasets that offer information in a single format, our reasoning traces are flexible, including timestamps and descriptions of key actions and logical steps. We evaluate both open-source and proprietary models on MINERVA and compare their reasoning traces to our ground truth annotations to identify common failure modes. From this analysis, we develop a taxonomy of errors specific to video reasoning, categorizing them into four main areas: perceptual correctness, temporal localization, logical reasoning, and completeness. We use this taxonomy to assess how both humans and language models evaluate reasoning outputs, revealing where automatic grading aligns with human judgment and where improvements are needed. Interestingly, we find that prompting language models with our rubric can enhance their performance in video reasoning, similar to the "let's think step-by-step" approach in text reasoning. In summary, we present the following contributions. MINERVA, a challenging video reasoning benchmark with 1,515 carefully crafted questions, each accompanied by 5 answer choices and detailed reasoning traces. An evaluation of various models on MINERVA, highlighting the importance of visual information. And a fine-grained error analysis that identifies common failure modes and establishes a taxonomy of reasoning errors, primarily related to temporal localization and visual perception. Our preliminary analysis of language model metrics indicates areas for future research. Section Summary. In this section, we introduce MINERVA, a challenging video reasoning benchmark consisting of 1,515 handcrafted questions that require complex multi-step reasoning and provide detailed reasoning traces for each question. We also evaluate various models on this dataset, identify common failure modes related to temporal localization and visual perception, and create a taxonomy of reasoning errors to guide future improvements in video understanding. Section: Related work. In this section, we discuss recent advancements in video question answering, video QA, datasets. Several new datasets have emerged, such as temporal bench and perception test, which include tasks like video QA, captioning, and grounding, but they primarily feature short videos, typically just a few minutes long. Similarly, CinePile and VideoVista focus on short content, averaging around 160 seconds, with Video Vista covering a wide range of tasks. Other datasets like InfiniBench and Neptune utilize semi-automatic methods for annotations, while our dataset is fully manually annotated. TVBench tackles the challenge of difficult answer candidates in video QA, highlighting the role of visual information. ETBench emphasizes understanding multiple events and time-sensitive information, using human-annotated videos up to 795 seconds long. VideoMe connects short and long-form content, with datasets like LVBench and Our Video extending to videos that last from 20 to 120 minutes or even longer. Unlike these benchmarks, our work not only provides final answers but also includes human-annotated reasoning traces, which will help future evaluations assess both reasoning processes and accuracy. We also note that few datasets offer additional information beyond final answers. For instance, Science QA provides science questions with accompanying lectures, which enhance performance with fewer data points. Some recent efforts have aimed to create automatic labeling systems that generate auxiliary information, but these often result in noisy data. Visual Cot and Video Espresso generate bounding box labels for images and videos, respectively, but they differ from our approach. VideoCoT, which aims to create text-based reasoning for videos, uses a semi-automatic pipeline, while we focus on a fully manually annotated dataset for evaluation. Additionally, the videos in VideoCoT are sourced from Kinetics 700, making them shorter and more limited in scope. As reasoning models have developed, there has been significant analysis of reasoning in text-only contexts, revealing that the correctness of answers does not always reflect correct reasoning. Previous studies have categorized evaluations into reference-based and reference-free methods, with reference-based evaluations proving more reliable. Our work contributes a high-quality dataset with reference annotations for video reasoning, which may encourage further research into both evaluation types. We also introduce MINERVA, our video QA dataset, which includes 1,515 challenging questions across videos of various lengths. Each question comes with 5 answer options and a detailed reasoning trace. Key features of our dataset include complex, multi-step questions, multimodal requirements, high-quality annotations, and intermediate reasoning traces that allow us to analyze model errors beyond final answers. We perform reference-based analysis of model outputs, which is more cost-effective than reference-free assessments. Our dataset features a wide range of video lengths, with the longest being 100 minutes and the shortest under 2 minutes, averaging 12 minutes. Each video has multiple questions, with an average of about 6.8 questions per video. The reasoning traces are detailed, averaging 92 words, and 99.6% include timestamps, with an average of 4 timestamps per trace. Section Summary. In this section, we review recent video QA datasets, highlighting their focus on short videos and automated annotations, while contrasting them with our fully manually annotated dataset, MINERVA, which includes complex questions and detailed reasoning traces. Our dataset not only facilitates error analysis through reference-based evaluations but also spans a wide range of video lengths, enhancing the understanding of model reasoning processes. Section: Dataset Construction. In this section, we outline our approach to constructing a dataset for multimodal models. As these models advance, creating challenging questions becomes more complex. We aim for questions that require multiple steps to solve and cannot be answered solely through speech or external knowledge. Our dataset construction involves several key steps. 1. Video selection. We choose video categories from YouTube that are suitable for our question criteria. 2. Manual annotation. Raters create questions, answers, and reasoning paths. 3. Quality review. Other raters review the questions for quality. 4. Adversarial filtering. We reduce textual bias by using consensus from various text-only models. For video selection, we focus on domains that support complex reasoning. We identify several categories. Short films. These are multi-event videos with storylines, avoiding mainstream movies to reduce bias. Sports and board games. Videos in this category allow for questions based on rules and player actions. Educational. We include STEM lectures, though they make up only a small portion of our dataset due to the dominance of speech. Lifestyle. Vlogs and how-to videos are included, as they often follow logical sequences and require spatial reasoning. In the annotation phase, raters propose intricate questions that engage at least two reasoning skills, such as temporal reasoning or spatial perception. Each annotation is verified by another rater, and we periodically review the annotations to ensure they align with our guidelines. To ensure quality and minimize biases, we filter out low-quality reasoning traces and address any potential text biases through adversarial filtering. This involves gathering consensus from various text-only models to avoid discarding challenging questions. We also benchmark several models, starting with blind baselines that use text-only prompts. We then test advanced video models, including top-performing open-source options and proprietary models from companies like Google and OpenAI. We aim to maximize the number of frames used in our experiments while comparing performance with and without OSR transcripts. Section Summary. In this section, we outline our dataset construction process for multimodal models, which includes selecting complex video domains, manually annotating questions and reasoning, and implementing quality reviews and adversarial filtering to mitigate biases. We focus on diverse video categories like short films, sports, educational content, and lifestyle vlogs to ensure questions require multi-step reasoning and cannot be answered solely through speech or external knowledge. Section: Prompts. In this section, we conduct an analysis on how different prompting styles affect MINERVA using our top model. We explore three prompting styles: I. Asking the model to answer questions directly. E. Requesting the model to reason step by step. And E. Providing the MINERVA rubric for video reasoning. The prompts are detailed in the appendix. We then apply the best results from this analysis to prompt all other baseline models, aiming to standardize prompts while also incorporating specific prompts from authors to give models an advantage. For implementation, we adhere to best practices from model authors. We sample video frames uniformly and create prompts by mixing them with timestamps. Since many questions refer to specific moments in the video, we also include automatic speech recognition (OSR) data with timestamps every 5 seconds. We ask models to present their answers in a format that can be easily processed. If a model fails to respond or if the response is not clear, we randomly assign an answer for accuracy calculations. Detailed settings are available in the appendix. Regarding multiple choice question (MCQ) performance, we present modality ablations, showing that baselines using only question answering (QAD) or OSR without visual data perform poorly, indicating that visual information is crucial for MINERVA. We observe that increasing the number of frames improves performance, with OSR providing additional benefits. A more detailed analysis of frame variation is included in the appendix. In our MCQ results, we find that the performance gap between open source and proprietary models has decreased, with Qwen 2.5-VL and Intern Video 2.5 surpassing Claude Sonnet. The Gemini 2.5 Pro thinking model achieves the highest score at 66.2%. Although performance is still below human levels, we believe MINERVA will serve as a valuable benchmark for video understanding. We also test the thinking mode of the Gemini 2.5 models, finding that enabling this mode enhances performance, especially as the number of frames increases. This indicates that reasoning about longer video content is essential for achieving high accuracy on MINERVA. We analyze model performance based on skill, video domain, and length. Models struggle most with counting questions, followed by counterfactuals and state changes. Gemini 2.5 Pro excels across all skills, while GPT 4.1 performs similarly for state changes and cause and effect questions. All models perform well with short films but face challenges with math videos. Human performance is generally high across skills, with the lowest scores in counting, and they perform well in most domains except for tech AI. We note that model performance declines as video length increases, similar to previous findings, while human performance is best for videos under 5 minutes. In our prompt analysis, we discover that asking the model to reason step by step significantly boosts MCQ accuracy. Interestingly, explicitly including the rubric in the prompt further enhances scores, with reasoning outputs also improving as evaluated by an automatic judge. This improvement requires minimal additional computation, suggesting that guiding models to reason according to our rubric can lead to better outcomes. Finally, we conduct a human study where raters, separate from those who annotated the data, answer the dataset questions. The results reveal a substantial gap between model and human performance, with the best model, Gemini 2.5 Pro Thinking, still nearly 30% behind human scores. Section Summary. In this section, we analyze the effects of different prompting styles on the MINERVA model, finding that step-by-step reasoning and providing a rubric significantly enhance accuracy. Our experiments reveal that while models struggle with longer videos and specific question types, the best-performing model, Gemini 2.5 Pro Thinking, still lags behind human performance by nearly 30%. Section: Assessing Methods for Video Reasoning. In this section, we explore ways to evaluate the step-by-step reasoning provided by multimodal models. While enhancing performance, prompting models for reasoning also boosts interpretability. However, objectively assessing the accuracy and usefulness of these reasoning steps remains a challenge. Human evaluations are often seen as the best standard, but they can be costly and time-consuming. Therefore, we also investigate assessments based on large language models, LLMs. We recognize that a reference-free assessment could evaluate reasoning without needing ground truth, but it would require access to the original video, which can be expensive as video length increases. Instead, we utilize reasoning traces from MINERVA for a reference-based analysis, which allows us to work in a more cost-effective text format. Unlike math or coding, where multiple solutions exist, video reasoning questions in MINERVA are more rigid, requiring precise identification of time segments and key information. Our ground truth reasoning traces have several characteristics. The number of steps varies, the traces are lengthy, and some steps are more critical than others. This complexity poses challenges for rule-based or embedding-based evaluations but is more suited for LLM-based assessments. We start by analyzing model outputs to categorize reasoning errors and then create a simple LLM-based judge to score video reasoning. Finally, we gather human evaluation scores for a subset of MINERVA and examine the correlation between model and human assessments. We propose a straightforward taxonomy of reasoning errors for video models tackling complex questions. By reviewing outputs from various models, we identify 4 main error categories. 1. Perceptual correctness. Errors in recognizing objects, actions, or events, including issues with automatic speech recognition or optical character recognition. 2. Temporal localization. Mistakes in pinpointing the correct time frames in the video needed to answer the question. 3. Logical reasoning. Errors in reasoning based on perceptual elements, including numerical mistakes. 4. Completeness. A reasoning trace is incomplete if it misses necessary steps to reach the correct answer. We provide examples of these errors in an appendix. Using these categories and a 3-point Likert scale, we develop a general rubric for evaluating reasoning traces from video models, which we call the MINERVA rubric. We found that a 3-point scale is easier for both humans and models to use consistently. Next, we assess human and model evaluations for a sample of model traces. We randomly select 200 questions from MINERVA and 2 model outputs for each question from the models Gemini 2.0 Flash, GPT-4o, and Qwen 2.5-VL. We then present these 400 model reasoning traces to human raters, along with question-answer pairs and ground truth reasoning traces, asking them to score each trace using the MINERVA rubric. Having the ground truth speeds up the process since raters do not need to watch potentially lengthy videos for each output. Detailed instructions for the raters are included in the appendix. For LLM-based assessments, we ask an LLM to score reasoning traces according to the MINERVA rubric, matching the scores given by human raters. We test both reference-based and reference-free prompts. Instructions for human raters are provided in the appendix, along with the specific prompt for the LLM assessment, which we refer to as MIRA, MINERVA Reasoning Assessment. All scores are normalized to a range between 0 and 1.